So to continue with this, let us go for what is called as Fermi-Dirac statistics. Fermi-Dirac statistics. FD statistics. FD statistics. FD statistics. This similar to Bose-Einstein statistics, only difference between this and the other one, the number of particles. The particles are called as fermions. Fermions. These particles are also identical but indistinguishable, and they have the spin that is half integral 1 by say 2, 1 by 3 and so on. The fermions you can say. Just a minute. They are having half integral spin. Fine. That is 1 by 3, 1 by say and so on. Electrons, protons, say neutrons are these particles. These fermions, they obey the Pauli's exclusion principle. Pauli's exclusion principle. They obey Pauli's exclusion principle. That means one particle in one cell, or it is having only one energy level. So the distribution function, number of particles distributed. So Ni are the number of particles distributed in Gi cells. That is given by this Gi factorial Ni factorial Gi minus Ni factorial. This is the relation here, you can say. Fine. Gi divided by Ni factorial Gi minus Ni factorial, and this is the distribution function. Once we have this distribution function, what is the energy distribution formula for this? What is called as Fermi-Dirac statistics. Ni is equal to Gi. Keep in mind, Gi are the cells, e to the power alpha plus Ei divided by Kt, that is 1 or Kt is beta plus 1. This is for Fermi-Dirac statistics. This is its distribution function. This is the energy distribution formula for Ni particles. Okay. So let us take 1 or 2 examples, or let us compare this. I'll write it here. Compare these 3 statistics. Okay, I'll write MB, BE and FD. Let us compare this first. MB means classical statistics, Maxwell-Boltzmann statistics. This is Bose-Einstein statistics, Fermi-Dirac statistics. Number 1 point here. In classical statistics or in Maxwell-Boltzmann statistics, the particles are identical and indistinguishable here. In other 2 statistics, that is BE and FD, particles are identical but they are indistinguishable. Right? Here the example of particles, that is molecules of the gas, here they are helium, or say photons, here electrons, neutrons, protons. These particles are called as fermions, this is called as bosons, and the classical particle here. In MB statistics, there is no restriction on the number of particles in a given cell. Here in B statistics also, there is no restriction on the number of particles in a given quantum state or a cell. But there is a restriction here in FD statistics, because these two statistics, they doesn't obey the Pauli exclusion principle, whereas this statistics obeys the Pauli exclusion principle. So one particle in one energy state. The number of ways how the energy is distributed, means particles are distributed, we have written the formulas for these three. So size of the cell, there is no restriction on the size of the cell here. There is a restriction, size of the cell is h cube, size of the cell is h cube here. V is equal to, or the volume of the cell, V is equal to h cube, V is equal to h cube, and there is no restriction here. If you write the distribution function, that is Gi for classical statistics, Gi raised to Ni upon, say, Ni factorial here. This is for classical statistics. For, say, Bose-Einstein statistics, it is Ni plus Gi, Ni plus, it is Ni plus Gi minus 1, Ni plus Gi minus 1 factorial divided by, thus, that is Ni factorial Gi minus 1 factorial. You can calculate using this, and similarly for this, it is Gi factorial divided by, say, it is Ni factorial into bracket Gi minus 1, Gi minus Ni, Gi minus Ni factorial. So energy distribution function you can write here. So these are some comparison of this. Now using this comparison, let us take some multiple choice questions. Now my question is, does Bose-Einstein, does bosons obey, or Bose-Einstein statistics obeys Pauli's exclusion principle, or bosons obey the Pauli's exclusion principle? Answer is no. MB statistics cannot obey the Bose-Pauli's exclusion principle. Bosons have spin. Say answer. Question is, bosons have spin. Either it is 0 or 1, because it is integral multiple of integer, or it is 0. Photons obeys which statistics? Photons obey which statistics? Photons obey Bose-Einstein statistics. Neutrons obeys Fermi-Dirac statistics. Spin of photon, based on this, if they ask the spin of photon, it is 0 or 1. Spin of photon. Spin of, say, neutron, it is half integer, right? It is half integer. Okay, so which statistics obeys Pauli's exclusion principle? They will give this 1, 2, 3, and fourth one is none of this. So Fermi-Dirac statistics obeys Pauli's exclusion. Let me take a simple example here. Say for example, Find the number of ways in which bosons may be, say, 3 bosons distributed in 4 cells. Find the number of ways in which 3 bosons distributed in 4 cells. Number of particles are given 3 and number of cells are given 4. How many ways we can have this? So this can be found out using this, that is, say, Ni using this. Fine. Ni plus Gi minus 1 factorial, okay, divided by, say, Ni factorial Gi minus 1 factorial. Now here this is how many ways we have to distribute Ni. The number of particles 3, number of cells are equal to 4. So let us substitute here. Ni is 3 plus Gi is 4 minus 1 factorial. Say Ni factorial, that is 3 factorial, Gi 4 minus 1 factorial. Here this will be 3 plus 4 is 7, 7 minus 1, 6 factorial, divided by 3 factorial, 4 minus 1, it is 3 factorial. Now I will distribute this, that is factorial means we have to write from this 6 into 5 into 4 into 3 into 2 into 1. Now this is 3 factorial, 3 into 2 into 1 into, say, 3 into 2 into 1. So these 3 into this gets cancelled. So we have to find this, that is, what is equal to 6 into 5 into 4 divided by 3 into 2 into 1. 6 5s are 30, 34s are 120, divided by 3 2s are 6. So 120 divided by 6, this will be 2 and it is. That means the number of ways we can distribute the 3 particles in 4 cells, there are 20 ways. There are 20 ways in which we can distribute this. Let's take for another example for fermions. Fermions, say fermions, that means I have to use that formula. Ni is equal to, say, 3. Ni, the number of particles are equal to 3 and number of cells are equal to Gi is equal to 4. So the formula which we need here for fermions, that is Gi factorial divided by Ni factorial Gi minus Ni factorial. Let us substitute for Gi. Gi is equal to 4 factorial, Ni is 3 factorial, Gi minus Ni, Gi is greater than Ni, so 4 minus 3 factorial. Let us solve this. 4 into 3 into 2 into 1 divided by 3 into 2 into 1. 4 minus 1, 4 minus 3 is 1. That is 1 here. So this gets cancelled. Simply, how many ways? 4 ways. That means one particle at a time will have one cell will have one particle at a time. The number of ways here we got equal to 4. Let's do this for both, that is MB statistics. Say Ni is equal to 3 Same example, Ni is equal to 3 and say Gi is equal to 4. So how many ways we can distribute the number of particles? 3 in Maxwell-Boltzmann statistics. So that is equal to Gi raised to Ni. Simple. Gi raised to Ni. Gi is 4. 4 raised to 3. So this 4 into 4 into 4, that is 64. How many ways? In a 64 ways, this 3 number of particles distributed in 4 cells. Number of ways are 64. Here only 4. In other case, it is 20. Only one example we have taken. Maybe they may not ask this as a numerical because no problems will be there, but we don't know. This you can't say it is a problem. They ask this. So go through such questions, okay, of multiple choice. I'll read one question here. Pauli's exclusion principle applies to. Pauli's exclusion principle applies to. My alternate answers are MB statistics, MB, say the other one FD, C, that is BE. D is all of this. D is all of this. So this is Pauli's exclusion principle obeyed in. Thus, okay. Say, according to FD statistics, I will frame a question here. According to FD, that is Fermi-Dirac statistics, 3 particles can be distributed in 4 energy states. Means cells. 3 particles, that is Ni is equal to 3 and Gi is equal to 4. So you can have this, and the number of ways the answers will be here. Already we have solved this. Okay, so answer, say alternate answer 16, say B is 4, say C is 3 because here is a number and D is 12. So answer is this. We have calculated this. So we can boson's value of spin. I'll write the question here. Boson's value of spin. Boson's value of spin. Alternate answers, 4 answers. Boson's value of spin. A is 0, say B, bosons here, B is 1, C is half, D is 0 or 1. What will be the answer? It can't be 0 alone, it can't be 1 alone, it can't be half because bosons they have integer spin. 0 or integer spin, and this is the correct answer here, 0 or 1. Fermions have the spin. Fermions have the spin. Fermions have the spin. Okay, this alternate answers are, say fermions have the spin. You can say A is equal to half, B is equal to say 0, C is equal to say 1, D is equal to say D is equal to anyone. You can write anyone here. Fermions, they have the half integer spin. Half integer spin, that is thus. The answer is this. This can't be, this can't be, this can't be. So this is answer. Similar questions you do practice I have completed your syllabus for this semester. Still, I will take 1 or 2 video classes on kinetic theory of gases. I will solve some multiple questions. Even I will upload them in video class. Right? Thank you.